morning everybody. This is our second lecture on reaction mechanism of coordination compounds. We will discuss the mechanism of aqueous reaction and base hydrolysis today. So if you remember the aqueous reaction, in aqueous reaction the coordinated ligand is replaced by water molecule. We have earlier discussed in detail how the coordinated ligand is replaced by water molecule in presence of acid. So if you remember that, we should take a complex this is pentamine chlorocobalt ion. This is allowed to react with acid in presence of water. The product is pentamine aqua, cobalt ion and chloride ion. So what should be the mechanism of this reaction? If we compare chloride, bromide and iodide, this is hardest and this is softest. If we compare the halides, chloride, bromide, and this is the hardest, this is the most hard, this will be least hard, or this will be least soft, this will be most soft. So if we start with a complex like this, this is pentamine chlorocobalt ion. And if it is allowed to react with hydronium ion, this equilibrium constant is Kh. Kh is the equilibrium constant, then you will get so here the chloride, which is the hardest base, is softest base. So the chloride, coordinated chloride, if we compare chloride and coordinated chloride, then coordinated chloride would be coordinated chloride. This will be softer in comparison to this, because the electron flow is taking place from chloride to cobalt 3 center. Cobalt 3 and chloride. So if you compare the hardness of this and coordinated chloride will be more hard in comparison to chloride. So if this complex reacts with acid, producing the chloride, coordinated chloride will be protonated, producing conjugate acid. Or we write here Ca, conjugate acid. So chloride ion can combine with H plus, producing HF. So this is conjugate acid of chloride. Conjugate acid of chloride is hydrogen chloride. Similarly, conjugate acid of coordinated chloride will be this complex. Now this complex, in presence of water in medium, rate determining step, this can produce product plus chloride. what should be the rate law? Now here we are talking of only acid dependent path. It can have also solvent dependent path. If there is solvent dependent path, this complex can combine with the solvent in a K0 path producing product. The coordinated fluid system can have acid dependent path. This is acid dependent path and this is solvent dependent path. If both the paths are present, K0 is solvent dependent rate constant, K is acid dependent rate constant. What is K0? K0 is solvent dependent rate constant. And K is acid dependent rate constant. So a mechanism can be like this. It may have solvent dependent path and acid dependent path. But if this path is negligible, K0 path is negligible, if the solvent dependent path is neglected, then the mechanism becomes simplified. Here, if it is not neglected, then what will have? What will be the mechanism? Mechanism rate will be Kh into conjugate acid equilibrium plus K0 into complex equilibrium. If the solvent dependent path is not neglected, then rate will be like this: Kh into concentration of conjugate acid plus K0 into concentration of the complex. If it is neglected, then the system becomes, if K0 is neglected, if solvent dependent path is neglected, then what should be the rate law? Rate law becomes much simpler. Here rate will be equal to Kh into conjugate acid equilibrium. It will be equation 1. The rate will depend on the concentration of the conjugate acid. Higher is the concentration of conjugate acid, higher will be the rate of the reaction. It depends. It will depend on the concentration of conjugate acid. Then, what is equilibrium constant? Kh. Kh is conjugate acid equilibrium by complex equilibrium into H plus equilibrium. H plus I am writing instead of hydrogen I am writing only H plus. To become more simple, it will make it more simple. Suppose we start with initial A moles per liter, initial B moles per liter. Initially this should be 0 moles per liter. At equilibrium, if this is A minus X moles per liter, this is B minus X moles per liter, this will be X mole per liter. At equilibrium, initial concentration of the complex, B the initial concentration of the acid, initial concentration of conjugate acid will be 0. At equilibrium, if this is A minus X mole per liter, this will be B minus X mole per liter, this will be X mole per liter. Here, what is the unit? So, unit will be, this is one concentration unit, one concentration unit, one concentration unit. The final unit will be mole inverse liter. Kh, unit of Kh will be mole inverse liter, because one concentration unit cancels. So 1 by concentration unit. So concentration is expressed in moles per liter. So unit of Kh will be mole inverse liter. If it is thermodynamic equilibrium constant, then these things will be expressed in activity. So there will be no unit. If you consider Kh as thermodynamic equilibrium constant, these things will be expressed in activity. Therefore, there will be no unit. But if you express in the concentration unit, then the unit of Kh will be mole inverse liter. So then this is going to be equation. Then conjugate acid equilibrium will be KH. KH is equilibrium constant. Equilibrium constant for the formation of conjugate acid. What is KH? KH is the equilibrium constant for the formation of conjugate acid. So conjugate acid equilibrium will be KH into complex equilibrium into H plus equilibrium. Then equation. Here C stands for, C is equal to complex. Let it be clear, C stands for complex. So if we substitute complex equilibrium from equation 3 in equation 1. If you substitute complex equilibrium from equation 3 in equation 1, then what would be rate? So rate would be equal to KH complex equilibrium into hydrogen ion equilibrium. This is equation 4. Now A is equal to complex total or initial concentration of the complex, and A minus X is equal to complex equilibrium, that is equilibrium concentration of the complex, and X is equal to conjugate acid equilibrium, that is equilibrium concentration of the conjugate acid. Please let it be clear, A is equal to complex total, initial concentration of the complex. A minus X is complex equilibrium, equilibrium concentration of the complex. X is conjugate acid equilibrium, that is equilibrium concentration of conjugate acid. We can write down mathematically A is equal to A minus X plus X. We can mathematically write down A is equal to A minus X plus X. What is A? A is the complex total or initial concentration of the complex. What is A minus X? Concentration of the complex at equilibrium, and what is X? Concentration of conjugate acid. So then write down complex total is equal to complex equilibrium plus conjugate acid equilibrium. This is our equation 5. Now substituting the value of conjugate acid from equation 3 in equation 5. Now here substituting conjugate acid equilibrium from equation 3 in equation 5. Then what you get? You get complex total is equal to complex equilibrium plus KH into complex equilibrium into hydrogen ion equilibrium. This is equation 6. Or complex equilibrium is common 1 plus KH into hydrogen ion equilibrium, or complex equilibrium will be equal to complex total by 1 plus KH into hydrogen ion equilibrium. This is equation 7. What is complex equilibrium? Complex equilibrium will be equal to complex total into 1 plus KH into hydrogen ion equilibrium. Why you are converting complex equilibrium into complex total? The reason is we do not know how much complex is at equilibrium, but we know how much complex you have taken initially. Experimentally we know how much complex you have taken initially. Therefore, complex equilibrium term has to be replaced by complex total term. Then substituting complex equilibrium. Substituting complex equilibrium from equation 7 in equation 4. What do you get? You get that will be equal to KH into KH complex total into hydrogen ion equilibrium by 1 plus KH into hydrogen ion equilibrium. Now still there is one hydrogen ion equilibrium term. This is our equation 8. Since the concentration of acid is much greater in comparison to concentration of the experimental, but you see concentration of acid is much more greater in comparison to concentration of the complex, because you have to maintain pseudo first order condition. So here the hydrogen ion total is far greater than complex total. Generally hydrogen ion total may be of the order of 0.1 molar and complex total may be of the order of 0.005 molar. Hydrogen ion concentration is 0.01 molar, this is 0.05 molar. This is much greater than this. Therefore, hydrogen ion total will be approximately equal to hydrogen ion equilibrium. How? This can be proved very easily, because if 10% reaction is taking place, 10% for 10% reaction, X value will be 0.0005. 10% of the complex consumption. 10% of the complex, if 10% of complex is hydrolyte, then the X value will be 0.0005. Then what is complex equilibrium? Complex equilibrium will be 0.005 minus 0.0005. And what is the hydrogen ion equilibrium? The hydrogen ion equilibrium will be 0.1 minus 0.0005, which is approximately equal to 0.1. Therefore, hydrogen ion equilibrium, and this is equal to hydrogen ion total. So therefore, hydrogen ion equilibrium is approximately equal to hydrogen ion total, but complex equilibrium is not equal to complex total, because there is 10% decrease in the concentration of the complex. Therefore, this equation, equation 8, can be changed to equation 8. Under this condition, equation 8 can be written as rate is equal to KH into complex total into hydrogen and total by 1 plus K into hydrogen and total. This is final rate. Equation 9. This is final rate. So what does this rate law indicate? The reaction will show first order dependence in complex total. Because there is no complex total term in the denominator. Numerator you have one complex total term. In the denominator you have no complex total term. And the reaction will show first fractional order dependence in hydrogen ion conservation. If this is the rate law, if this rate law is valid, the reaction will show fractional order dependence in hydrogen ion conservation and unit order dependence in complex total. But generally kH into hydrogen ion total is much less than 1. Because kH value will be less, so this will be less than 1. Under this condition, what will be rate law? So rate will be equal to kH into kH complex total into hydrogen ion total. If this is neglected in comparing to 1, then the reaction will show first order dependence in complex total and first order dependence in hydrogen ion total. That means if you plot the rate versus hydrogen ion total, when complex total is constant, then it should be linear passing through origin, and slope will be kh into complex total. So if complex total conservation is kept constant and hydrogen ion conservation is varied, then the rate versus hydrogen ion total plot will be linear passing through origin.
Fractional dependency on H plus tab. Keep Daniel sir.
Fractional order dependence, how will you know? You can know like this. You need to plot rate versus hydrogen ion total. If the nature of the plot is like this, then there is fractional order dependence. If hydrogen ion concentration is less, then this will show first order dependence. If the hydrogen ion concentration is high, then this will show zero order dependence. In this region there is zero order dependence, because by increasing hydrogen you are not getting, rate is not increasing.
Yes sir.
But this portion rate is increasing when you increase hydrogen ion total. So here first order, here zero order, in the middle region there will be fractional order. Okay?
Thank you.
Just like Macleas-Menten plot. But we cannot take rate. Rate is to be converted into K observed rate constant. The observed rate constant is calculated by taking down the complex total at various time intervals. So therefore rate is equal to, so rate will be equal to K observed into complex total. Because rate will depend on complex total concentration. Rate will be K observed into complex total. This is 11. So if you compare this with this, compare equation 9 and 11, we can write down K observed into complex total is equal to kh into complex total into hydrogen ion total by 1 plus kh into hydrogen ion. So complex total cancels. K observed will be equal to kh adjoint total by 1 plus kth into adjoint total. This is the rate law in the light of K observed. Rate is replaced by K observed, then this will be rate law. We calculate K observed. Always pseudo fast order rate constants we calculate. So we calculate K observed. Unit is second inverse. So experimental you will get this. So if you take the reciprocal, what is the reciprocal of this? So 1 by K observed will be 1 by kth plus 1 by kth into 1 by adjoint total. This is equation 30. So this is y, this is c, and this is mx. This is of the form y equal to mx plus c. This term is m, this term is m, this term is c. Then if you plot 1 by K observed versus 1 by adjoint total, then you should get a straight line like this. OA is equal to intercept. Then let it be I will be equal to 1 by kh. And what is kh? K is the reciprocal of intercept. From the reciprocal of intercept, we get kh. And what is slope? Slope S will be equal to 1 by kh into kh. So intercept by slope will give you the value of kh, equilibrium constant kh. So from intercept the slope, we get the value of kh. From the reciprocal of intercept, we get the value of this rate constant. Rate constant, this is equilibrium constant. So you are getting equilibrium constant and rate constant. So if you carry out the reaction in more than 4 temperature or minimum 4 temperatures, we can calculate activation parameter and standard enthalpy and entropy changes. We can calculate. We can calculate using Eyring equation. Ln K2 by T is equal to ln Kb by X plus delta star by R minus delta star by R into 1 by K. So here Kb is Boltzmann constant, H is Planck's constant. So if you multiply this with minus 1, then minus ln K2 is second order rate constant will be minus ln Kb by X minus del star by R plus del S. So what should be the nature of the plot? So here, nature of the plot, it will have a negative intercept. From the intercept OA is equal to minus log AB by H minus del S double dagger by R. And what is slope? Slope will be from the intercept and slope. From the intercept you get the value of activation entropy. From the slope you get the value of activation enthalpy. So then what is activation free energy change? Activation free energy change so at 25 degree you can also get the value of activation free energy change. If you know the value of delta star, if you know the value of delta S double dagger, delta S double dagger, delta S double dagger, you can get the value of delta S double dagger of activation free energy change. And since we have determined the equilibrium constant, we can also, we know that delta G0 equal to delta H0 minus T delta S0, and delta G0 is equal to minus RT ln kh. So if you substitute this value here, then what you get? You get minus RT ln kh is equal to delta H0 minus T delta S0. So ln kh minus ln kh is equal to minus delta H0 ln kh will be minus delta 0 by R into 1 by T plus delta S0 by R. So if you multiply minus 1 and divide with RT, so here will be RT. So in minus 1 means this will be term will be minus, this term will be plus, divided by RT. So ln kh is equal to minus del 0 by R into 1 by T plus del S0 by R. So if you plot ln kh versus 1 by T. So slope, from the slope you get the value of delta H0, from intercept is equal to delta H0 by R. From slope is minus delta H0 by R. So in this way we can calculate thermodynamic parameters and also activation parameter for the acid dialysis reaction. For MSc student, up to this is okay. For research, you have to know, calculate activation parameters and also standard enthalpy change and entropy change. So this completes the mechanism of acid hydrolysis. So next we will discuss the mechanism of base hydrolysis. We will discuss DCB mechanism, dissociative conjugate base mechanism. Mechanisms of base SN1C or DCB. What is SN1C? Substitution nucleophilic unimolecular conjugate base mechanism. SN1C means substitution nucleophilic unimolecular conjugate base mechanism. So now we have to know what is the conjugate base. So if you take ammonia, suppose you take acetic acid, let us take acetic acid plus hydroxide ion. So you get acetate ion plus water. Acetic acid combining with hydroxide ion producing acetate ion plus water. Then this is conjugate base. If you take ammonia, when ammonia is behaving like acid, it will combine with hydroxide ion producing amide. This is conjugate base. Amide formation does not take place with hydroxide ion, but it can take place in presence of sodium. So if you take ammonia, liquid ammonia plus sodium, you get soda made. NaNH2 plus hydrogen. This reaction you all know. So this amide is formed. NH2 minus. NH2 minus is called amide. But this is amide. So amide is the conjugate base of ammonia. When ammonia is behaving like acid, then its conjugate base will be amide. When the ammonia behaves like base, ammonia plus H plus, giving rise to ammonia, this is the conjugate acid. The conjugate acid of ammonia is ammonia, the conjugate base of ammonia is amide. Now if you compare ammonia and coordinated ammonia, if you compare ammonia and coordinated ammonia. Now coordinated ammonia will be here, it will be more acidic. It will be more acidic in comparison to ammonia. If you compare only ammonia and coordinated ammonia, if we compare ammonia and coordinated ammonia will be more acidic in comparison to ammonia. Why? Because the ammonia is now coordinated to cobalt 3 center. So electron flow is taking place from nitrogen center to cobalt 3 center. So acidic nature of the NH proton will increase. Therefore, coordinated ammonia will be more acidic than ammonia itself. So, we take a complex compound. So here the pentamine chlorocobaltriane is cobalt is in plus 3 state. So pentamine chlorocobaltriane is allowed to react with hydroxide ion. The corresponding equilibrium constant is Kc. It will produce so since amide is formed and amide is negatively charged, so one negative charge, second negative charge, here three positive charge, so overall charge will be plus 1. So this is the conjugate base. Conjugate base of this, if this is considered as acid, this is will be the conjugate base. If this is acid, then that will be conjugate base. The next step is conjugate base. RDS, rate determining step, produces an intermediate the leaving group chloride is removed. Leaving group chloride is removed. This is the intermediate. This is intermediate is unstable and this will combine with water very fast. Here the coordination number is changing from 6 to here coordination number of point was 6, 4 plus 1, 5 plus 1, 6. Here the coordination number is 5, unstable. This will produces and combines with water very fast. And you get this is the product. Because from water, amide takes a proton from water producing ammonia and OH minus hydroxide ion is attached here. So this is the product. So three-step process. First step, formation of conjugate base. Second step, slowest step, producing intermediate. Intermediate combines with water fast, producing the product. Now in the rate determining step, since only one species is involved, this is unimolecular reaction. In the rate determining step, only one species is there, therefore this will be a unimolecular reaction. And since coordinated chloride is replaced by hydroxide ion, this is a hydrolysis. This is nucleophilic substitution reaction. Since the coordinated chloride is replaced by hydroxide ion, this is a nucleophilic substitution reaction. Since at the rate determining step only one species is there, the unimolecular reaction. Since this mechanism takes place with the formation of conjugate base, this is called SN1CB, substitution nucleophilic conjugate base mechanism, or DCB. Nowadays it is called DCB, dissociative conjugate base mechanism. Now a proton expulsion takes place from the trans to chloride. If you add chloride here, if chloride here is transposition is this, from transposition the hydrogen ion expulsion will take place, leading to formation of conjugate base. If this is blocked, then only it will expulsion will take place from cis position.
Transposition टा kind हुई?
Transposition एक हमारी जितना negative charge हवा, इधर negative charge है और negative repulsion बड़ी बैठी repulsion कम होगा. So this will be more stabilized. So now we'll derive the mechanism of the base hydrolysis. So suppose at equilibrium, this is A minus X mole per liter. This is B minus X mole per liter. This will be X mole per liter. At equilibrium, initial concentration of the complex is A. So at equilibrium, we have A minus X mole per liter. This will be B minus B, the initial concentration of hydroxide. This will be B minus X mole per liter, and this will be X mole per liter. Better we write down mole, or there will be confusion. We write down mole. So what will be rate? So rate will be equal to KCB into conjugate base equilibrium. Here we are using equilibrium approximation. There are two types of system by which you can derive the rate law. One is equilibrium approximation, another is steady state approximation. Here we are using equilibrium approximation process to derive the rate law. So what will be rate? Rate will be rate constant. Rate constant into concentration of the conjugate base. This is our conjugate base. This is nothing but conjugate base. And what is KCB? KCB will be equal to conjugate base equilibrium by complex equilibrium into hydroxide ion equilibrium. What is C? C stands for complex. This is equation 2. So what should be unit? So unit will be mole inverse liter. Because one concentration unit, another concentration unit, so only one concentration unit is left, so unit of KCB will be mole inverse liter. So we can write down conjugate base equilibrium will be equal to KCB into complex equilibrium into hydroxide ion equilibrium. This is equation. Substituting conjugate base equilibrium in equation 1. So here this data is substituted here. Then what you get? We get the rate is equal to KCB into KCB. Complex equilibrium into hydroxide ion equilibrium. Equation 4. Now, like earlier situation, we can write down A equal to A minus X plus X. That means complex total is equal to complex equilibrium plus conjugate base equilibrium. Equation 5. Substituting conjugate base equilibrium from equation 4 in equation 3, sorry. Equation 3 in equation 4. equation 5. Equation 3 रू equation 5 रे हमें substitute करें. Then what you get? Complex total will be equal to complex equilibrium plus KCB into complex equilibrium into hydroxide equilibrium. Or complex equilibrium is common 1 plus KCB into hydroxide equilibrium. Therefore, complex equilibrium will be equal to complex total by 1 plus KCB into hydroxide equilibrium. This is equation 6. So substituting equation 6, substituting complex equilibrium from equation 6 in equation 4. What you get? You get rate equal to KCB into KCB complex total into hydroxide equilibrium by 1 plus KCB into hydroxide equilibrium. Similar in the earlier case, we know the hydroxide total is far greater than पूरा बंद कर दें. Hydroxide total, since hydroxide total is much greater than complex total. Why it is greater? Because pseudo-phosphoric condition is maintained. We keep hydroxide concentration as 0.1 molar and complex total maybe 0.005 molar. Here hydroxide concentration is 0.1 molar and complex total is 0.005 molar. Therefore, the equilibrium, hydroxide equilibrium can be replaced by hydroxide total. So, hydroxide equilibrium is approximately equal to hydroxide total. So, this is equation 7. So, equation 7 can be rewritten as equation 7 can be written as equation 8 when hydroxide equilibrium is equal to hydroxide total. Therefore, what will be rate? So rate will be equal to KCB into KCB into complex total by into hydroxide total by 1 plus KCB into hydroxide total. Now this is our equation 8. 7 over equation 8. Now pK of coordinated ammonia is about 16. Hence, Ka will be 10 to the power minus 16. Coordinated ammonia. What is coordinated ammonia? Cobalt 3. This is our coordinated ammonia. pK of coordinated ammonia is about 16. Hence, K will be 10 to the power minus 16. And what is Kcb? So, Kcb is equal to K by Kw. That is K is the dissociation constant of coordinated ammonia. Kw is ionic product of water. So this is your 10 to the power minus 16 by 10 to the power minus 14, that is 10 to the power minus 2. If hydroxide ion concentration is 1 molar, then Kcb into hydroxide ion total will be 10 to the power minus 2 into 10 to the power minus 1. That is 10 to the power minus 3. 10 to the power minus 3 is much smaller than 1. Since 10 to the power minus 3 is much smaller than 1, equation 8 can be written as rate is equal to Kcb into Kcb complex total into hydrogen ion total. That means the reaction will show first order dependence in complex and first order dependence in hydroxide ion total. So this can be converted into K observed situation since rate is equal to K observed into complex total. This is our equation equation 9. This is equation 9. This is equation 10. So therefore we can write down K observed. We will equal Kcb. If you compare this equation with this, complex total will cancel. So K observed will be Kcb into Kcb into hydroxide ion total. The unit of this is second inverse. Unit of this is mole inverse liter. So product of these two is second order rate constant. This is second inverse. Kcb unit is second inverse. Kcb unit is mole inverse liter. So Kcb into Kcb unit will be mole inverse second inverse liter. Or you can write down second inverse mole inverse liter. So this is nothing but unit of second order rate constant, that is equal to K2. K2 is second order rate constant. So you can write down K observed is equal to K2 into hydroxide ion total. Finally, you can write down like this: K observed is equal to K2 into hydroxide ion total. So, what should be the nature of the plot? So, if we plot K observed versus hydrogen ion total, hydroxide ion total, you should get state line like this. T1, T2, T3. T3 is greater than T2 is greater than T1. So second order rate constant here will be greater than this. This will be higher. Second order rate constant of this will be greater than this. This will be greater than this. So this will be the nature of the plot. So the SN1C mechanism is only valid if the metal ion is coordinated to a base having dissociable proton. SN1C mechanism will only be valid if the complex has a dissociable proton. Suppose you take a complex like this, COCN all type chloride. This will be 3 minus. 5 cyanide ions are there, 1 chloride ion is there. There is no NH proton. So since there is no NH proton, no conjugate base formation is possible. If the no conjugate base formation takes place, then SN1C mechanism will not operate. Here, if we plot K observed versus hydroxide ion total, you may get a linear plot. Because there is no conjugate base, so by increasing hydroxide ion concentration, the conjugate base concentration will not increase. Because according to Lee-Chatterjee principle, if you increase the hydroxide ion concentration, conjugate base concentration will increase. But here, for this type of complex, or take this type of pyridine complex, here there will be 2 plus. 5 pyridine units are coordinated to covalent center linking group is chloride. For these 2 complexes, K observed versus Y channel product should be linear. Because conjugate base formation is not possible, by increasing hydroxide ion concentration, the K observed will almost remain constant. So this, if K observed versus Y plot is linear, parallel to the x-axis, then SN1CP mechanism is not operating. If K observed versus hydroxide ion total plot is linear at different temperatures, it is linear passing through origin, then SN1C mechanism may be operating. So this is the difference in which situation SN1C mechanism is operating, in which situation SN1C mechanism is not operating. So similarly, in base of disease, if we determine the second order rate constant at different temperatures, we can also calculate activation parameters using iron equation. If you calculate, if you plot K observed versus Y channel total, that means you have to calculate observed rate constant at different hydroxide ion concentration.
Minimum 3 temperatures.
Minimum 3 or many आजकल तो 4-5 करेगा 3 रे हो नहीं 4 and above 5 temperature. Then you can calculate the activation parameter using iron equation. So in the next lecture we will discuss what are the factors controlling acid hydrolysis and base hydrolysis. Last one is mechanism of anation reaction. कितना समय चल
1 hour.
हाँ anation reaction आई जाए. Now in the previous lecture, last lecture, we have discussed what is Anderson reaction. If the coordinated water is substituted by anion, that is Anderson. If it is substituted by neutral molecule, then that is substitution reaction. In the Anderson reaction, ion pair formation will take place. In the substitution reaction, outer sphere complex formation will take place. Let us take example. Suppose we take this CO both pipe plus chloride this is ion pair. The water, this chloride ion will remain in the outer sphere. Inner sphere you have this system. So this is a tri-positive, this is a negative charge. Positive, negative, so therefore there will be Coulombic force of attraction, that is called ion pair. If you take a neutral molecule, suppose plus ammonia, here outer sphere constant, outer sphere complex, yes. Outer sphere complex formation equilibrium constant. This is outer sphere complex. So mechanism is almost same for Anderson, and only the equilibrium constants and rate constants are in name is different. So lot of work can be done in Anderson reaction or substitution reaction. Earlier at Mohanty we have done a lot of substitution reaction for cobalt 3 system, chromium 3 system, rhodium 3 system, platinum 2 system, etc. Now if you take soluble peptides, then you can do good work in Anderson reaction. Soluble peptides. So first step is the formation of ion pair, and then K Anderson, we get product. This is the product. So I have told you that in Anderson reaction is reverse of aqueous. Here if you plot, here the versus chloride ion, here the versus lambda. Observance versus lambda. This is time t equal to 0, this is the observance will go on increasing in Anderson reaction because the extinction coefficient of this complex is around 48 and this will be around 72. So therefore, observance at 500 nanometer will go on increasing. Extinction coefficient at 500 nanometer is 48. This is 72. Therefore, observance will go on increasing. Initial the final observance will be higher in compared to initial observance. So here K observed will be 1 by T ln observance infinity minus observance 0 by observance T minus observance 0. From this equation, we can calculate K observed. Observance infinity minus observance 0, because observance infinity is higher than observance 0. So you have to use this equation to calculate K observed. So what would be, so at equilibrium, this is A minus X moles per liter, this is B minus X mole per liter, this will be X mole per liter. So A can be written as A minus X plus X. So therefore, complex total will be equal to complex equilibrium plus ampere equilibrium. Complex total will be complex equilibrium plus ampere equilibrium. KIP, ampere formation equilibrium constant will be ampere equilibrium by complex equilibrium into chloride equilibrium. This is equation 1. So ampere equilibrium will be equal to KIP into complex equilibrium into chloride equilibrium. This is equation 2. Substituting equation 2, this may be equation 3. In equation 2, substituting ampere equilibrium from 2 in, what do you get? Complex total will be equal to complex equilibrium plus KIP into complex equilibrium into chloride equation 4. Chloride equilibrium is common, 1 plus KIP into chloride equilibrium, equation 5. So complex equilibrium is equal to complex total by 1 plus KIP into chloride equilibrium. This is equation 6. And what is the rate? The rate will be equal to Anderson rate constant into ampere equilibrium constant. Substituting ampere equilibrium from equation 2 in equation 7. What do you get? The rate is equal to Kn KIP into complex equilibrium into chloride equilibrium, equation 8. Substituting the value of complex equilibrium from equation 6 in equation 7. What do you get? You get rate is equal to K answer KIP complex total chloride equilibrium by 1 plus KIP into chloride. This is equation 8. 8, equation 9. Since chloride and total is far greater than complex total. In Anderson reaction, chloride and concentration may be of the order of 1 molar, or maybe say 0.5 molar, and complex total may be 0.005 molar. This is much higher. This should become much higher. To maintain pseudo-Carter condition, this should be higher than this. Since chloride total is greater than complex total, chloride and equilibrium will be approximately equal to chloride and total. Because if there is a 10% reaction, then the X value will be 0.0005. X value will be 0.005. Then what is chloride and equilibrium? So chloride and equilibrium will be equal to 0.5 minus 0.0005. So therefore, chloride and equilibrium will be approximately, this is very small in comparison to 0.5. So chloride and equilibrium is approximately equal to chloride and total. So here equation 9 can be rewritten as equation 10. How? So rate will be K Anderson, Ki, complex total into chloride and total by 1 plus Ki into chloride and total. What does this indicate? This rate law indicates, this is equation 11. This rate law indicates the reaction will show first order dependence in complex and fractional order dependence in chloride. Because the numerator you have chloride total, in the denominator also you have chloride total, therefore the reaction will show fractional order dependence in chloride total and first order dependence in complex total. So if you plot rate versus chloride and total, you plot rate versus chloride and total at fixed complex total, then the reaction, then the plot will be like this. So at the initial stage, when the chloride and concentration is low, the reaction will show first order dependence. At high chloride and total, the reaction will show zero order dependence. So in between this, the reaction will be fractional order. So let us convert this into K observed. Rate loss will be converted into K observed. Since the rate is equal to K observed into complex total, equation 12. If we compare equation 11 and equation 12, what you get? K observed into complex total is equal to K Anderson Ki into complex total into chloride and total by 1 plus KIP into chloride and total. So complex total cancel. K observed will be equal to K Anderson KIP into chloride total by 1 plus Ki into chloride total. This is equation 13. If you take reciprocal of equation 13, if you take reciprocal of equation 13, then what you get? You get 1 by K observed, 1 by K Anderson, plus 1 by K Anderson, KIP, into 1 by chloride total. This is of the form y equal to mx plus c. What is y? Y is equal to 1 by K observed. What is c? C is equal to 1 by Anderson rate constant. What is m? M is 1 by Anderson rate constant into K. What is x? X is equal to 1 by chloride total. So if the reaction is carried out at different chloride ion total, then 1 by K observed versus 1 by chloride ion total should be linear. So OA intercept will be 1 by K. So reciprocal, what is K Anderson? K Anderson, you get K Anderson from reciprocal of intercept. And what is slope? Slope S will be equal to 1 by K Anderson into Ki. So intercept by slope will give you the anchor formation equilibrium constant. So if you carry out the Anderson rate constant at 4 different temperatures or 4 and above different temperatures, we can also calculate activation parameters, and from activation parameter we can suggest the mechanism as ID or IA, and we can also calculate del G0, del H0 and del S0 if you calculate TIP at 4 different temperatures. So from the kinetics you get the equilibrium constant data at different temperature. From the equilibrium constant data at different temperature we can calculate del G0, del H0, del S0. From this rate constant you can calculate activation free energy change at 25 degree, activation enthalpy change and activation entropy change. From activation entropy change we can calculate, we can know whether the mechanism is IA or ID. So lot of information you get from the, if you carry out the reaction at different temperatures, this Anderson reaction, if it is carried out at different temperature, we get lot of informations. Now what is the prospect of this type of work? Instead of chloride ion, if we take any water soluble peptides, then this type of work can be carried out and may be published. So there are some questions. The trans-dichloro BC39 quad 3 complex, what will be the conjugate base? Draw the structure of the interpretive. You see, hydrolysis is slower than base hydrolysis. Why? Why acid hydrolysis is slower than base hydrolysis? Why? The cis reacted at a slower rate, at a faster rate. Faster rate than transaction. The cis complex acted at a faster rate than the transaction. But reverse is the situation. Or base hydrolysis. Why? KCB equal to K by K. How can you prove that KCB equal to K by K? These are some of the questions that you should think and try to solve. How are you?